Good morning, everyone. Welcome to today's presentation. I'm excited to discuss S-block elements with you. The title of today's talk is S-block elements, and there's a lot to explore. We'll cover their properties, uses, and what makes them unique. So let's dive in and get started. Now, moving on to slide 2, which covers the applications of alkali metals. As we explore this, it's important to recognize that these metals are quite versatile and have a variety of uses across different industries. For example, alkali metals like sodium and potassium are essential in the production of chemicals, including soaps and glass. They also play a crucial role in the manufacturing of fertilizers, which are vital for agriculture. Additionally, some alkali metals are used in batteries, especially lithium, which powers many portable electronic devices and electric vehicles today. Understanding these applications helps us appreciate the significance of alkali metals beyond their chemical properties, and also sets the stage for discussing their characteristics and behaviors later in this presentation. Welcome to the introduction. On this slide, I want to take a moment to explain the key points thoroughly, but in a conversational way. We'll be highlighting the most important concepts that set the stage for the rest of our presentation. As we go through, I'll connect these points to the overall theme, helping you see how everything fits together and why it matters. My goal is to make sure the foundation is clear so we can build on it as we move forward. Let's dive in and explore these initial ideas together. Let's take a closer look at the electronic configuration of S-block elements. For alkali metals, the general configuration is noble gas ns1, which means they have one electron in their outermost s orbital. On the other hand, alkaline earth metals have the configuration noble gas ns2, indicating they have two electrons in that same s orbital. Now, these elements are part of the long form of the periodic table, which is divided into 4 blocks: S, P, D, and F. The key point here is that the elements in group I and group II, which are the alkali and alkaline earth metals, receive their last electron in the s orbital. Because of this, they are collectively called S-block elements. This classification helps us understand their chemical behavior and how they fit into the overall periodic table. So, the placement in the S-block isn't just about where they are on the table. It reflects their fundamental electronic structure, which influences their reactivity and properties. Let's take a closer look at the characteristics and properties of alkali metals. These elements are quite fascinating because they share some common traits that set them apart. For starters, they are highly reactive, especially with water, which makes them very interesting to study in terms of chemical behavior. Their reactivity increases as you move down the group, so lithium is less reactive than cesium or francium. Alkali metals are also characterized by having low melting points and low densities, which means they are quite soft and can even be cut with a knife, unlike most metals you're used to. These physical properties are closely linked to their atomic structure, which is relatively simple and has only one electron in their outermost shell. This single valence electron is the reason behind their high reactivity. They tend to lose that electron easily to achieve a stable electronic configuration. Connecting this to the overall theme of the periodic table, alkali metals help us understand how atomic structure influences chemical properties and reactivity. So, in summary, their softness, low melting points, low densities, and high reactivity are key characteristics that define alkali metals and make them unique among the elements. Let's take a closer look at the atomic and ionic radii of alkali metals. These metals have the largest sizes within their period on the periodic table. As we move across a period, the atomic size decreases, but when we go down a group, the size increases. That's because with each new element, an additional electron shell is added, making the atom larger. Now, when these atoms form monovalent ions, such as M+, they are actually smaller than the parent atom. This is because losing an electron reduces electron-electron repulsion and allows the remaining electrons to be pulled closer to the nucleus. Interestingly, as we go down the group from lithium to cesium, these ions get larger again, reflecting the increase in atomic size. All alkali metals share a similar electronic configuration, with one valence electron in the ns1 orbital, outside a noble gas core. This loosely held outer electron makes these metals highly electropositive, meaning they tend to lose electrons easily. That's why they readily form M+ ions and are never found in a free, uncombined state in nature. They're always part of compounds. So, understanding these atomic and ionic size trends helps us grasp the unique reactivity and behavior of alkali metals in various chemical contexts. Now, let's talk about how alkali metals and their salts give a distinctive color to a flame. When you heat an alkali metal or its salt, especially chlorides, which are more volatile in a flame, the electrons in the metal atoms get excited easily to higher energy levels by absorbing energy. Then, as these electrons return to their original, or ground, state, they release that absorbed energy in the form of light. This emitted light falls within the visible spectrum, creating a characteristic color for each metal. This phenomenon is what we call flame coloration, and it's a useful way to identify different alkali metals. For example, lithium produces a crimson red flame, sodium shows a golden yellow, and potassium gives off a pale violet hue. Now, as we move down the group from lithium to potassium, the size of the atoms increases. Because the atoms get larger, the attraction between the nucleus and the outermost electrons becomes weaker. This weaker attraction means it takes less energy to remove an electron, so the ionization enthalpy decreases down the group. In fact, alkali metals have relatively low ionization enthalpies compared to other elements, which makes them more reactive and easier to excite in a flame. This decreasing ionization enthalpy down the group explains why the characteristic flame colors are so prominent and easily observed. Let's take a closer look at the atomic and physical properties of the alkali metals. These elements, which include lithium, sodium, potassium, rubidium, cesium, and francium, are known for their distinctive characteristics. One of the most notable features is their low atomic numbers, which means they have relatively few protons and electrons compared to other elements. This low atomic number contributes to their high reactivity. In terms of physical properties, alkali metals are soft and can often be cut with a knife, especially lithium and sodium. They tend to have low melting points compared to most metals, which is quite interesting because it makes them more malleable and easier to shape. You'll also notice that as you go down the group, their atomic size and physical softness increase. Another key point is their high reactivity, which is driven by their single valence electron. This makes them eager to lose that electron and form positive ions, or cations. That reactivity increases as you move down the group, which is why cesium and francium are so explosive when exposed to water. Understanding these properties is essential because it connects to their chemical behaviors and their uses in various industries. These properties help explain why alkali metals are so important in things like batteries, pharmaceuticals, and even in certain types of research. So, their atomic and physical characteristics are not just interesting on their own. They're fundamental to understanding how these elements behave and where they can be applied. Let's take a closer look at chemical properties. These are the characteristics that describe how substances behave at a molecular level. Understanding these properties helps us predict how chemicals will react with one another. For example, some chemicals are reactive, meaning they readily undergo chemical reactions, while others are more stable. This is important because it influences how we handle and store different substances safely. It also connects to the overall theme of understanding material behavior, which is crucial in fields like chemistry, manufacturing, and safety protocols. Recognizing these properties allows us to work more effectively and avoid potential hazards. So, in essence, chemical properties give us the foundational knowledge to manipulate and utilize materials responsibly. Let's look at how alkali metals react with oxygen and air. When potassium reacts with oxygen, it forms potassium superoxide, KO2. Similarly, sodium reacts to form sodium peroxide, NuTwo2. Lithium, when heated with excess air, forms lithium oxide, LiTwo. Interestingly, The pattern is that lithium tends to form the normal oxide, sodium forms peroxide, and potassium, rubidium, and cesium form superoxides, which have the general formula MO2. So, the general reaction for these metals with oxygen can be summarized as 4M plus O2 giving 2M2O, where M stands for any alkali metal like Li, Na, K, Rb, or Cs. Now, because of their reactivity, alkali metals tarnish in air. This tarnishing is due to the formation of oxides or hydroxides on their surface. When they burn in air, they form different types of oxides, depending on how much oxygen they react with. If the oxygen is limited, they form their normal oxides. With the formula M2O, this highlights how reactive these metals are and how their reaction products vary with the conditions. Let's take a closer look at how alkali metals react with water. The general reaction can be summarized as Ta-Us plus 2H2O, which produces 2Li-O and hydrogen gas. This reaction is quite characteristic of all alkali metals. They react violently with water, forming a metal hydroxide and releasing hydrogen gas. Now, among these metals, lithium is actually the least reactive. It does react quickly with water, but not as explosively as the others. On the other hand, potassium, rubidium, and cesium are much more reactive and tend to react so violently that they can even cause explosions. Understanding this reactivity trend is important, as it ties back to the overall theme of alkali metals, chemical behavior, and their tendencies to form compounds. Let's take a look at how lithium hydride reacts with water. When LiH encounters water, it reacts to produce lithium hydroxide and hydrogen gas. This reaction is a good example of how alkali metal hydrides behave with moisture. They tend to react readily, forming hydroxides and releasing hydrogen. Moving on to the general reactivity of these hydrides, you'll notice that they generally react with hydrogen gas itself. For example, if you take a generic metal, let's say M, and expose it to hydrogen at around 673 Kelvin, it forms a crystalline hydride, which is typically colorless. It's important to highlight that all alkali metal hydrides are ionic solids, and they tend to have high melting points. This ionic nature is a key factor because it influences their stability and reactivity. So, in terms of overall reactivity towards hydrogen, alkali metal hydrides are quite reactive and can be formed under specific conditions, such as high temperature, and they are good examples of ionic compounds that play a significant role in hydrogen chemistry and storage. This ties into the broader theme of how metals and their compounds interact with hydrogen, which is fundamental in fields like energy storage and materials science. Let's take a closer look at the general formula for alkali metal halides, which is 2M plus X2 2MX. Here, M represents any of the alkali metals like lithium, sodium, potassium, rubidium, or cesium, and X stands for halogens such as fluorine, chlorine, bromine, or iodine. What's important to note is that these metals react very vigorously with halogens. When they do, they form these ionic crystalline solids called metal halides, which have the general formula MX. This reaction highlights the high reactivity of alkali metals, especially towards halogens, and it's a key part of understanding their chemistry. It also connects to the overall theme of how alkali metals tend to form ionic bonds and stable compounds with nonmetals, particularly halogens. The blue color of the solution is primarily due to the presence of the ammoniated electron. This electron absorbs energy in the visible region of light, which gives the solution its distinctive blue hue. It's quite fascinating how this tiny particle can influence the color so significantly. These solutions are paramagnetic, meaning they are attracted to magnetic fields, which is an interesting property linked to the unpaired electrons. When left to stand, these solutions slowly release hydrogen gas, leading to the formation of amide compounds. The general reaction involves the metal reacting with ammonia to form complex ions and free electrons, like this. M, X plus Y, NH3 gives us M, NH3 X plus and E, NH3 Y minus. When alkali metals dissolve in liquid ammonia, they produce these deep blue, conducting solutions. This process showcases how solubility in liquid ammonia allows for unique and highly conductive metal ammonia solutions, highlighting the special interactions between metals and ammonia in this context. Let's take a closer look at some of the key applications of this technology. As we've discussed throughout the presentation, understanding how these concepts apply in real-world scenarios is crucial. On this slide, you'll see a few main points. First, the technology can be used to enhance data analysis, making it faster and more accurate. This is especially important in fields like healthcare and finance, where timely insights can make a big difference. Second, it can improve automation processes, streamlining operations and reducing human error. This means more efficiency and reliability in various industries. Lastly, these applications demonstrate how the core principles we've covered can be adapted to solve complex problems across different sectors. Overall, these examples tie back to our main theme: leveraging innovative solutions to create smarter, more effective systems. Rubidium and cesium, along with their compounds, have relatively limited applications. However, cesium metal vapor is quite important because it's used in atomic clocks. These clocks are incredibly precise, so much so that they serve as the official time standards worldwide. Moving on to potassium, it's less commonly used as a free metal compared to sodium. But potassium salts are actually produced in large quantities for fertilizer manufacturing, which is essential for agriculture. Now, lithium metal has a few specialized uses. It's used in certain lightweight alloys and also as a reactant in organic synthesis, which is quite important in chemistry. Most notably, lithium is critical in making lightweight batteries. Think of the batteries in our smartphones and electric vehicles. That's a major application. Lastly, sodium is by far the most important alkali metal in industry. We use hundreds of thousands of tons of sodium compounds each year. These include common salt, baking soda, sodium carbonate, and caustic soda, each playing a vital role in various industrial processes and everyday products. So overall, while some alkali metals have niche uses, sodium's role in industry is truly central. Let's take a moment to look at the references. These are the sources that support the information we've discussed today. They provide credibility and allow anyone interested to explore the topics further. It's important to recognize the key studies and reports that have shaped our understanding. By citing these references, we also ensure transparency and academic integrity. Remember, these sources are the backbone of our research and conclusions. If you want to dive deeper into any specific point, these references are the best starting point. Thank you for paying attention to this essential part of our presentation. Let's take a moment to acknowledge some of the key references that underpin our understanding of inorganic chemistry. First, we have Housecroft and Sharp's Inorganic Chemistry textbook, now in its second edition, published by Pearson Education Limited. This book is a comprehensive resource that covers fundamental concepts and recent advancements in inorganic chemistry. Next, we have Cotton, Wilkinson, and Gauss's Basic Inorganic Chemistry, third edition, which is a classic in the field, known for its clear explanations and foundational principles. Finally, Atkins, Overton, Rourke, Weller, and Armstrong's Inorganic Chemistry, fourth edition, published by Oxford University Press in 2006, is another authoritative source that provides detailed insights into the subject. These references are essential because they form the backbone of much of our current knowledge, helping us connect theoretical concepts to practical applications. They also highlight the importance of rigorous study and continual learning in inorganic chemistry. By understanding these core resources, we're better equipped to appreciate the complexities and beauty of inorganic compounds and reactions, which ties directly into the overall theme of this presentation: embracing the depth and diversity of inorganic chemistry.